engineers. So Philo, hopefully you're still there in the laboratory. We want a bit of a tour. We want to see a little bit about where you're at. But if you could first start off by saying who you are, how you got into what you're doing, and then explain quite where you are. There you are. We can see you now.
Thank you, Toby. Welcome to Building 46. That is the home of the Welding Engineering and Laser Processing Center. I work here as a senior lecturer in additive manufacturing here. I've been in Cranfield for about 10 years. I came as a master's student, actually, a double degree student. I started doing my MSc thesis on this topic of wire and arc additive manufacturing, which is what I'm going to talk about today. And then I decided to make it my career, which is why I'm still here today. I mentioned additive. Thank you. I mentioned additive manufacturing. What is AM, or as you might know it already, 3D printing? As the name suggests, is a process which is based on building objects in a layer-by-layer manner. And it's actually counterposed to other manufacturing technologies, like, for example, subtractive manufacturing. In order to have an AM or a 3D printing process, we need three main ingredients: a heat source, a motion system, and some sort of feedstock. And if we combine these three in a number of ways, we give origin to a wide range of processes. For example, we can look at processes based on a bed of pre-placed powder, which by using a laser heat source can generate highly complicated, optimized structures which are net shape. So in theory, the geometry is exactly the one you want it to be as soon as the manufacturing process is finished. However, these processes are extremely constrained in terms of cost. Machinery is expensive, raw materials are expensive, and also speed and size, which are both very, very small. If we look at the slide that Chris can put up right now, there is quite a convenient way of comparing a variety of different AM processes. And if we go back to what Richard was saying, in terms of attracting the business opportunities for parts which are large, big engineering structures where cost savings are important and excellent mechanical properties in the as-built condition is key, as well as part scalability, we are left pretty much with the choice of wire and arc AM, or WAAM, as a process of choice. And that's what we have been doing here at Cranfield since 2006. Thank you, Chris. So as the name suggests, WAAM is based on wire instead of powder as feedstock. And this enables substantial scalability of the part that we can make. We can make them much faster. Instead of building at 100 grams per hour, we can, for example, build up to 15 kilograms per hour. We can make these parts as big as you want, as I will show you later, and of course for a much cheaper way. Here we've got only a few of the many demonstrator parts that we've made throughout the years for our research partners. For example, this outboard landing gear rib that we made more or less 8 years ago for Bombardier. Traditionally, this part would be machined out of solid or of very rough forgings. You would start from a billet of over 250 kilograms in mass. You would spend quite a lot of time machining it away, removing this fantastic titanium in the foremost swarf until you are left with the final geometry. And of course, that swarf can be recycled, but just to give you an idea, we might buy billets for 60 pounds per kilogram, and we sell that scrap for 60 pence per kilogram. So there is quite a lot of waste in money associated with that. By doing it in additive, first of all, we can compress the lead time associated with forging. Typically, you would have to wait 12, 14, 16 months for the forging to be delivered, plus the machining. While in additive, which is a process that's digital in nature, all we need in theory is a starting substrate and some wire as a feedstock, and we can build any shape that we want, provided we've got the initial CAD file. And so we can build this object in less than 30 hours plus machining. The reason why I keep mentioning machining is that our processes are so-called near net shape, meaning that the geometry out of the printing process is not quite the final one. A finished machining operation is required, but even so, we save quite a lot of time and a lot of money.
Philo, can I ask you a question? There's a question just come up.
Certainly.
It says, sounds like the resistance and adoption of WAAM comes from uncertainty in industry. Do you think that once several industries adopt WAAM in the mainstream, the manufacturing technique will boom?
Yes, at the moment, the reason why WAAM is not becoming mainstream just yet is that we've been very ambitious in targeting highly critical components. So we are not building small brackets for your television in the business class of an aircraft. We are building landing gear ribs or wing spars or highly important and structural elements. And therefore, before we can see this process rolled out in industry, we need to build that confidence in the structural integrity. Having said that, there has been quite the upkeep of WAAM in industrial design and civil engineering, and I think early next year a bridge which has been 3D printed will be installed in the red light district in Amsterdam actually.
Wow.
So WAAM is getting out there, and at this point in time we are working very closely with the OEMs, for example in this case aircraft manufacturers. We are about to start making a 200 kilograms landing gear rib in one of the cells here on campus in this building, and before we started with the proper manufacturing of this landing gear rib, we've done a couple of test pieces to make sure that certain features could be produced with the required integrity, and that's the typical journey that we put in practice.
I think Rosa has a question for you, Philo, if you can tolerate another question.
Yes, please.
Indeed, it was picking up some of the points that you were making earlier, Philo. You were saying that actually this process cuts out some of the waste, which we know is huge in some of the processes that you've been describing. It also makes things an awful lot faster. So already we can see that there's a competitive advantage for those manufacturers who apply it. But I would say that there is also an environmental impact that we need to think about. Certainly, it sounds to me as though you will be helping their environmental footprint, their impact on this earth that we all share, which sounds like a good thing. But one quick question. How do you recycle the products at the end of their use?
Good question.
It depends very much on the alloy that we are talking about. Actually, one of the reasons why titanium 64, which is the alloy that we've used for this material, is indeed the workhorse of the aerospace industry, is that once you have machined it away in the form of swarf, it can actually be recycled in a straightforward way. It is still quite energy intensive as a process, but it can be recycled. The same applies to most of the steel alloys and to some of the aluminum alloys. The challenges are for some special aluminum alloys which have been alloyed with some rare earths, or, as I will show you later, when we build structures made of several materials into one. And this is very much subject of painstaking research in other departments here on the university.
Great, thank you.
Super, thank you.
As you were touching upon the topic of emissions, let me give you some number. If we could switch from design for manufacturing to design for function, for example, by optimizing the shape of an object and reducing its weight, let's say by 1 kilogram, and this part was supposed to fly on an aircraft, just with that 1 kilogram we could save over 100 liters of fuel per year, which is more than 400 kilograms of CO2.
That's
so
what
we are working really closely with the industries in order to maximize these benefits in terms of flying object, but also in terms of objects which are here on the ground. I'm going to give you an example of this pressure tank. Actually, this is for space applications, but we have made several more for other sorts of applications. In this case, we can enable a number of advantages from a business point of view. First of all, if made traditionally, this tank would be made out of 3 different components. You've got the main ring, which is machined out of a forged ring. Then you've got the bottom dome, which is machined from a separate billet. And then here you would have a conduit, which is where the fluid is drawn out from. Instead, again, by maximizing the manufacturing capability of additive, we've decided to start from a commercially available rod, really easy to get hold of. That's our substrate. We then printed on it the dome, and then we continue with the deposition of the actual main body of the cylinder. So instead of having 3 separated components and the associated supply chain, now we can do everything in one go. Then we go from the preform made by WAAM to the finished machine component, and by doing so we can reduce the amount of titanium which is wasted by over 200 kilograms for every tank that we made. The tank also happens to be 60% cheaper to make, and it could be made really in a number of hours as opposed to several months. And just for your information, that's how the tank will look like after it's been finished machined. In particular, this actually is a fuel tank for a satellite. Another attractive point for this component was that because you are no longer constrained by the set of forging tooling that you need to have if you go down the traditional route, now you can change the shape and the size of your tank to match the requirements of the mission. So again, you can minimize the amount of fuel that you take to space. And again, each kilogram that flies to space is about 10,000 pounds. So if you can reduce some weight, you're also reducing your expenditure.
Can I ask you one more question, Philo? Another question has just come in. Do you have experience in duplex stainless steels? What are the challenges for this material?
We have deposited some of it. It's not quite as mature as other alloys like titanium-64. The challenge is in that particular class of steel is to achieve the right ratio of the various microstructure which you would have at room temperature once you're done with the 3D printing processes. And in particular, the corrosion properties depend on this ratio. And that's quite hard for us to achieve because our first preoccupation is to achieve the right geometry and to do so without producing defects. But we've got quite a lot of interest from our industry partners in the oil and gas and processing industry. So it's something that we are very actively working on, also by tuning the heat input that we provide using multiple energy sources, as well as developing new materials for this process. Because so far we've been using traditionally and commercially available welding wires, and this is no longer welding. The kit might look the same, but actually is a very different way to go about making parts. As we were talking about oil and gas just now, that's one of the most challenging parts we have made. It's an elbow for a flow loop. Typically, this part would be made as a pipe, and then it would be bent once it's been taken to high temperature, and then you have to apply a protective layer to mitigate the risk of corrosion. We've done this shape in one go by additive. The idea is that if the designer gave us the final shape, the final optimized design of the entire flow loop, this component would be no longer made out of several 90-degree bends, which are then joined together to straight bit to take the fluid from A to B, but we could have a nice elongated component which minimizes the pressure losses in the duct itself. And then crucially, because our process is open in nature, we can feed more than one feedstock at the same point of deposition. And in a related project, we have proven that we could build some of these shapes already with the protective layer for corrosion resistance inside, so that you have one step for both materials that give you the right geometry and the right properties.
We have another question about machining, if you can take that one. As the WAAM process evolves in capability, what do you think would be the major hurdles in integrating it with conventional processes like machining?
From the practical experiments that we have done so far, as we move more and more towards real case study, you have to keep in mind that we try to minimize the amount of material that we deposit. This means that we've got our initial CAD file, and we normally apply an envelope of 1 to 2 millimeters around it to enable the finished machining of the waviness. And therefore, it is quite critical that when you are taking the part out of the WAAM system into your normal machining center, be it a lathe or a milling machine, you position it in the right position, otherwise you would not be cleaning up the material where you want it to clean. But of course, in our case, digital technologies, for example, laser scanning and other metrology methods help us, because we can deposit the material, take a nice scan of it in a quick and inexpensive way, and then we know exactly how to set up that part on the machining center. And of course, between one and the other, typically we would have to recur to a stress relieving heat treatment to reduce the residual stress and the internal tension, but these are established processes that have been around for decades. As I was mentioning multi-materials, I'm just going to give you a quick example of a specimen made in a graded way from steel to a copper-based alloy. Provided that the two materials are metallurgically compatible and they expand and contract in a comparable way, actually it's quite straightforward for us to go from one to the other. We have already achieved it, for example, going from steel to Invar for carbon fiber reinforced polymers tooling. So in this case, not for the production of the actual part, but for indirect application, the tooling, but also for more exotic applications, for example, for the nuclear fusion industry, where we can go from moly to tungsten to tantalum and so on, which is something that you can see here. And then finally, in terms of going forward, looking at how we can expand the geometrical capability of this process, we've been working very recently on dies for automotive application. This in particular is for the press forming of the A, B, and C pillar of your car chassis, as well as using other heat source, like in this case, where we can deposit using a laser instead of an arc, and we can deposit much thinner structures which crucially do not require any finish machining after they've been deposited. At this point, I think you guys must have had enough of the parts and probably want to see the machines where these parts are made.
I want to see, what does a typical machine look like? Can you show us one of those?
So, as I said, 3 ingredients, motion system, feedstock, and heat source. Typically, we like to use anthropomorphic robotic arms to provide the system, which is what you can see on both sides of me. These anthropomorphic robotic arms are most likely what have also built and assembled the car that you drive every day to go to work. So they are really established bits of kit, very reliable and easy to source. We can configure them in a number of ways. We have been chasing the possibility of making larger and larger and larger components. So in order to enable that, we said, let's stick them onto tracks so that they can slide as they print. And this process, or this approach, proved to be quite successful. The overall breadth of this cell is around about 10 meters. And I think in 2016, we were able to print a 6 meters long aluminum spar as a feasibility study. And as far as we know, that is still the world's biggest part ever 3D printed in metal in one go.
Wow.
The other attractive point of robots is that they are very flexible in nature, and therefore we can equip them with automatic tool changers. For example, in this case, what you can see on the left-hand side is where the magic really happens. This is our so-called end effector. At the center of it, at the heart of it, if you wish, there is a plasma torch, which is where the heat is generated. And then what you can see around it, it's a box. It's a special box that we called local shielding device. Now, for most reactive materials like titanium, typically you have to print them or weld them under inert atmosphere, and this can be either provided by argon or nitrogen or helium, or even further by pulling a vacuum inside the entire chamber. And of course, that's very much possible, but it presents challenges in terms of scalability. Imagine having a bag or a chamber around the entire kit that I'm working in at the moment. That would be very impractical. So we developed this box, which thanks to a clever design of plenum chambers and laminar flow tubes, produces that inert atmosphere only where the material is hot enough to need it, therefore at the bottom of its surface. And once the shielding device has moved away, we know that the material is cold enough not to get oxidated, therefore pick up oxygen anymore. And in this way, we've been able to print structures for fast jets, for example, Typhoon, that were over 2 meters in width and 1.5 meters in length, which is again a world first. Once we've got this mechanical housing.
Cut in there?
Certainly.
You say a world first. It's really great for any business to be able to say that. But as I look at the kit that's surrounding you there, Philo, I see KUKA robots. We're all, I think, pretty familiar with them on every advanced manufacturing factory floor these days. But then you talk about this is the box where the magic happens. Now, if I am a manufacturer, and I've certainly heard what you said about how this technology can really improve my performance, where am I actually going to get my hands on that wonderful box of tricks that you've just been talking about? And who am I going to be able to find who can keep it working for me? How am I going to be able to fit it within my business so that my staff can use it? You know, there's lots and lots of questions around that little box of magic that you've shown us.
It's a very good question, and that's exactly the journey we've been through and the questions that we have been asked by our industry partners. We've been working on this technology, as I said, since 2006. And in order to prove that it was viable, we had to develop all of these aspects in this center. And after so long, we finally have got enough confidence that we can bring them to the market, which is why in June last year, we have incorporated a spin-off company called WAAM 3D Limited, whose mission is indeed to enable a smooth implementation of the WAAM process. And to do so, we want to provide an integrated ecosystem to our potential customer, which hopefully will have all the answers to the questions you have just asked. So first of all, we are already sourcing the manufacture of the end effector, which has the shielding device, some adjustment of the wire positioning, as well as some sensors to monitor the geometry that are not yet available commercially. And in fact, in this particular case, we can call this a nice story of interdepartmental collaboration because these sensors were developed by our colleagues in the Fronius group. We have designed the entire software which does the toolpath planning, the calculation of the process parameters, and ultimately runs the machine. And also we're providing training and business case developments to our end users. So that is exactly what we want to do, because if you're providing only the machine or only the software or only part building services, you are helping your customer only in a fraction of the real way.
So Philo, I've got a question there, or rather, for those of you who just joined the session and wondering quite what it is that you're joined into, you're at Cranfield University, live. You're also with the Institute of Mechanical Engineers, the IMechE, who you may know it. I want to find out what that blue thing is and what it's hiding behind you there. Maybe Chris can give us a pan. But before you tell me that, Philo, there's another question just come on live onto the session. Without standardization, the industry will not accept the AM products easily. What are the latest activities regarding standardization of AM products? If that question
there is
makes
quite
sense.
a number of initiatives around the UK, the EU, and also the US. In the UK, the British Standard Institute has been quite active. I've been involved personally in 3 committees, one on the inspection, one on the raw materials, and one on the design of the machines. I've also contributed to writing some design guidelines for DED, so Directed Energy Deposition IM, which is the category WAAM belongs to, so that the designer of the future know how to design their parts best for this process. And then also a number of colleagues are involved in some committees of ISO or ISTM, in particular the F42, where standardization is really making good progress. That's a very valid point. We're doing our best by proving that technology is good in terms of integrity and properties, and then the standard hopefully will keep the community happy from a legal point of view and will make everything a little bit more normalized, which is what we would very much welcome.
Wonderful, Philo, thank you very much. We don't have a great deal more time, but tell us what's behind you under that blue tarpaulin, if we can have a little look at that area. Chris?
So actually, Toby, if I was able to tell you what's under here, then this part would not be covered in this blue cover. We work really hard in order to produce state-of-the-art component and to establish ourselves as a world leading institute. And so sometimes we need to take protective measure, because certain things that we've developed in terms of how to mitigate distortion and manage residual stress are quite unique. And
so you're saying that's secret? We can't see, we're not allowed to see that.
I can tell you what we're about to build. It's a cantilever beam. It will be 5 meters long for architectural application. I will be able to show the part once it's done, but at the moment we need to keep it under wrap because we don't want to disclose the way we are getting there.
Well, we haven't got a great deal more time, but any chance you could quickly show us a little bit more about the entire laboratory that you're in there here at Cranfield?
Yes, so this is only one of the 10 facilities that we have in the lab, and I think Chris has got a nice video which can give an overview of some of the other cells. Some of them are based on various other heat sources like arc or lasers, and the lab today is very quiet because we needed to do the filming, but normally there is a lot of activity going on. It's about 35 people of us in the lab doing experiments day in, day out. And sometimes it's stressful, but it's quite rewarding at the same time, because every day we find something new and we share it with our industry partners or we publish it. And it's very nice to work in this lab here in Building 46.
Philo, thank you very much. I got one last question that's online here. How do the mechanical properties of WAAM components stack up against those traditionally manufactured?
For most alloys, actually, we are just a bit shy of the properties for the equivalent forged material, and that's because we are using feedstocks and materials which were indeed developed and designed for forging. But actually, in additive, you are somehow in between the casting and the forging way of processing metals. So, in an ideal world, we would start from working with materials that have been designed for this process. In the interim, one of the things that we are doing here at Cranfield is to combine the additive processing with a mechanical treatment, in this particular case using a machine hammer pinning process. And what we do with this machine is introducing strain and stored energy in the crystals of the material which has just solidified, just like you would do in a forging operation. And then the subsequent heat provided by the deposition will trigger a change in microstructure. So at the moment we have actually proven that for a wide range of alloys like maraging steel, Inconel 718 or titanium 64, we can produce properties that are comparable, if not better, than the equivalent forged alloy. At the core of this is the baseline excellent structural integrity that we have. As I said, wire is clean and normally yields structures that are 100% dense. So even without the mechanical treatment, we've got a very good starting point to begin with.
Wonderful, thank you. I think, Rosa, you had a very brief question. We're running out of time, but a brief question.
I did. I was fascinated to hear how you're working through your upward supply chain on this, because standards are one thing, but actually making sure that the people who are buying stuff from you are convinced is a very big deal too, not always the same issue.
Good point. Philo,
Yeah.
I'm going to just come around, just a parting thought. If you had to leave the audience who have joined us here live at Cranfield University, a parting comment or question even, what would that be from you?
So I think, drawing from my personal experience, as I said, I've been here for 10 years and I thought about leaving several times, maybe to go back to somewhere warmer or with better food. And actually, in the last 4 or 5 years especially, I've had the constant feeling that this was finally kicking off, and it's just been getting bigger and bigger and bigger, and we've been getting more and more traction. And what I would like to say is that this way of making things is definitely going to change the way we manufacture metallic objects around the world because of a number of different business reasons, environmental reasons, and so on. So we're all very excited, and I ask you to keep an eye on Cranfield and on WAAM 3D because in the next 2 to 5 years, this will really take a massive step in the industry. And hopefully my dream is to print a part here, stick it on an aircraft in an hangar next door, and take off from the airstrip here at Cranfield, and come back in one piece, of course.
Of course, no small ambition there. Philo, thank you very much indeed for your time here. And those of you intrigued as to what Philo was standing in there, please get yourself to Cranfield. Start your journey with us. We have